Okay. Yeah, so this section is all about proteins, and the kind of like way that this chapter, I guess, is segmented is that it kind of starts by going like roughly in order from like you start with, so you kind of start with amino acids, right? And then from those you build up and you get a primary structure. Okay, and then this is kind of like the main focus of the chapter, right? Because this is where the most of the chemistry is, or at least like the reaction chemistry, and then after that you can build up secondary structure, and then you could build up tertiary and quaternary. But for one thing, the chapter like those aren't so relevant for this class, and also chances are you guys have seen those in other classes already, or will at some point in some biochemistry class. So the main focus is really going to be, I think, here and amino acids, these two. So yeah, I mean, we kind of start off with amino acids and how to make them, right? And I think there's 3 ways of synthesizing amino acids, or at least 3 common ways. So why don't you guys go ahead and list those off, or think of whatever comes to mind.
Reductive amination.
Yeah.
The transamination. And I don't know the third one.
The second one was what?
Oh, transamination. The alpha something is the third one.
Amination of alpha halo acids.
Yeah.
And then Strecker synthesis is one also.
Yeah. So Strecker is also there. Transamination is like, in some sense, is actually the most relevant one because it's the one that happens in biological systems. Although it's which one of these? I think it's similar to alpha halo acid. Whatever I wrote here, I don't know what this word is. Alpha halo acid amination. That's what it says. Yeah. So I think it's similar to this one. I can't remember exactly the details. This is what happens biologically. Because almost all, like biologically, most nitrogen, or most like NH2 is found in glutamate, or sorry, glutamine. Glutamine is, for whatever reason, just biologically like the kind of really accessible form of nitrogen. So the name glutamine might suggest that there's an amine involved, but right, you have glutamine and there's this nitrogen here. That's like a terminal amine, which you can use to it kind of just holds the amines, and then you could stick it on most other, or tons of other not amino acids, but things that will soon become amino acids. So like yeah, and so you could give this to other stuff, and then this will become amino acids. Okay. But in the lab, if we're just doing like bulk syntheses of amino acids, then, you know, we could do this other stuff. So here we could do reductive amination, which is like if we have this alpha halo acid, this alpha keto acid, and you know, on this end it could be whatever. I guess in this case I'll call it R because that's like a reasonable thing to do. In general, when we're talking about amino acids, the structure of it will look like this. Everybody also draws these a different way, but this is the like way that I personally do it. So this is an amino acid. In general, the L form is the biologically occurring one. So we have an L amino acid, and so I always draw the nitrogen on the left, the acid part on the right, and then this R group up top. If you want to be like very accurate, this should be a plus and this should be a minus, and there should be no hydrogen here, because in solution, right, it's usually found as a Zwitter ion, meaning that it has both a plus and minus charge, but it not a huge deal. So we have this alpha keto acid, right? And then we just literally do reductive amination on it, which you guys have seen and learned before already. So, right, 1, give it NH3, 2, give it one of the reductive amination reducing agents. If you got, I don't know if you guys remember these. You could pick your favorite one of choice. I think there's one that's like BH3CN, like sodium borocyanohydride or something like this. The 3 might be here or here. I can't remember exactly which one, but whatever your thing of choice is, and then, well, you remember the mechanism for this, right? It forms an imine and then it reduces. So there we go, and that's it. You have acid, amine, 1 carbon in the middle, R group. That's an amino acid. Okay, so then we could do alpha halo acid amination. So this is another way to do it, right? Here in this case, we could even start out with just an acid, right? And then get a halo acid by what reaction?
The Hell's Bollard, something
Yeah,
with
the
B.
HVZ thing.
Yeah.
Yeah, Helvold, Zelinsky, HVZ, which uses something like bromine and PBr3, and then maybe water at the end. Hold on. Can't remember the exact details of it, right? But you just do HVZ, and then we're here, right? And okay, just hit it with, you know, a whole ton of ammonia, because this is a secondary carbon, right? And you can't completely forget from SN2 that those don't react great with nucleophiles. So, well, we get here, and then, whoop, same thing. So, yeah, that works pretty nicely. This should be an NH2, right? Yeah, this is another good way to do it. It does require that you have this carbon here, which, like, yeah, but that's one thing. And then lastly, you could do the Strecker synthesis, which is kind of like a nice quick way of doing it. And so let's see if I can remember this. So you need acetaldehyde, or more generally, you might be able to use anything with an R group here. So maybe it doesn't have to be acetaldehyde. It might just have to be some aldehyde. in general, and then you add a cyano group and probably NH3. I think so. Because the idea is that you want to turn this into an amine, and then right, and then have this CN. And then you can cleave this CN with acid. So this is a two-step thing. So first you form this this thing here with the amine and then the cyano group, and then from there you cleave the cyano group with acid. NH2, right? Yeah, there's a hydrogen here. There's always a hydrogen, and then we've added that extra carbon that we needed, and so that's also an amino acid. Yeah. So this is a pretty fancy way of doing it. This is like none of these intermediate steps are new, but doing it sort of together and combining all of them is a new thing that we haven't really done before. So this is a cool way to make amino acids. Okay. Yeah. I think that's all of them. Let's see. I was looking through the book earlier even, and now I'm looking at it right now too, and there's this whole section on reactions, and they tell you like, oh, you could like, you could have like some amino acid, and you could esterify it, or like you could acylate this end, right? And like, okay, those are like not really new reactions. Like those, I mean, that like this is a nucleophile, that this is an amino acid or a carboxylic acid, so you could do all the reactions that you could on there normally. This is not like a really profound sort of thing. Let's see, there are a few. So okay, yeah, there's a reaction with ninhydrin, which is that one's okay. Well, okay, these are boring, right? Boring. There's a reaction that occurs with ninhydrin, which I didn't watch the lecture fully, so I'm not sure how much Dr. Tong talked about it, but this is like maybe he mentioned, this is like the stuff that they used to put on crime scenes, because you could spray it, and then if there's any protein anywhere, then it'll like cleave the protein, and or it'll react in this way, and then it turns purple, and so then you could like, flash a light on it, and you could see where there's blood or something. So this is like kind of why this whole thing was developed. And so you could take some amino acid, and I guess you need 2 of these things, this ninhydrin, and the structure of it is ugly, of course. Like here we go, right? And then this is like yeah, so apparently that's pyridine, right? And the point is you get this dye at the end, which, whatever, and then you get CO2 gas plus an aldehyde. Okay, cool, right? And so the main point is that you get this dye. In fact, the dye is purple. So very cool. And you could actually use this dye to do some analysis on proteins, because you could break down your protein all the way, and then do like electrophoresis or chromatography of some sort on all those amino acids that you have left over, and then mix it with dye, and the amount of amino acid that there is will correspond to how much dye you've produced. So you can get an idea, like a quantitative idea of what your composition of amino acids is in your protein. So this is an actual useful thing, besides just crime scenes. So yeah, this is like kind of the only new reaction, but it's sort of just one that you have to memorize. I guess not the only new reaction. There's another one, which has to do with the Edmond degradation, which is kind of like one of the two other big things left. So so the Edmond degradation, is one thing. It turns out that, I mean, even to this day, sequencing proteins is like incredibly hard. There's like no good way of doing it. These days, a lot of people use NMR or mass spec and kind of like, you know, use some really fancy computational stuff to look at protein composition, but even then it's still really quite hard. To the point that like taking a picture, like doing X-ray diffraction is one of the most reliable ways that we have even of figuring out the structure, combined with, of course, like looking at the nucleic acids, right? But Edmond degradation is a good way that they did it in the past. And then there's also, the book doesn't talk about it much. It has a question relating to it, but also there's also Sanger sequencing is another like historical way of doing it. I mentioned this largely because Sanger was like I don't know how like interested you guys are in the history of this sort of stuff, but like Sanger was a huge deal. He's, I think, one of the few people to have won 2 Nobel Prizes for sequencing a protein, and then the way that we sequence nucleic acids, or at least like the traditional way, is based off of him. He almost got a 3rd one for almost being the first to sequence RNA. So his way of doing proteins wasn't the best, but he was a big deal, and so I feel like he deserves an honorable mention here. But I guess Edmond degradation is the one that stuck around. So here we you have this NH2, and then here you have like your R group. It's going the other way because it's pointing down this time. Okay, yeah, right. And there's all this other stuff. And so from here you give it this this new reagent, which is phenyl NCS, so phenyl isothiocyanate. So this group is called isothiocyanate. Okay, and then this guy is going to react onto the carbon. And then there's this whole complicated mechanism, which I wouldn't expect that you need to know because it's quite complicated. But luckily, if you do need to know it, you have the book at your disposal. But the point is that from there, it winds up being, you wind up with this really, really specific structure. And so it's like this, and then there's an S, and then there's a carbonyl, right? And then this R group is hanging off here. So we started with this R group here, and now it's over here. And you could see where the backbone, this is where that whole amino acid was. And we're left with the rest of the structure. We just pulled one. So this was like R1. Then here we have R2. And we keep going. Okay, so this is like, yeah, this whole thing is the backbone of the ending amino acid. And I can make that clearer. So this whole structure is now this thing. Ooh. Oh boy. Yeah. Okay. And so, and then these sorts of structures here are very well classified, and so you could just isolate it and like take its melting point or something, and that'll tell you it's which amino acid you just pulled off, and then you kind of work your way down the chain, right? And yeah, okay. And then there's one more thing, which is what is called solid phase peptide synthesis. Okay. And so here what you do is you make this special resin called Merrifield resin. My Orgo 2 professor always talked about Merrifield resin because I think he was like, you know, buddy with Merrifield, and so so he always talked about this thing. And so the structure of it is that they take styrene, which is this. So this is styrene, like of polystyrene fame. And so then they put a carbon with a chlorine group on there. Okay. And so this is p-chloromethylstyrene. It doesn't matter, right? The point is that you get this polymer. And then every once in a while you'll get the p-chloromethyl of this polymer. Like just a small amount because you don't really need much. And then the nitrogen terminus, the amino side of your protein can attack. Right. And so here, you know, this is like it's a benzylic leaving group, right? So it's a good it's a good electrophile, and so you could just take it off. And that kind of attaches your protein onto your solid, like the beads of resin that you make, because this makes like a sort of like beads or like some kind of polymer. Okay. And then, oh, actually, sorry, wrong side. Yeah, I was thinking something was up. So this is the wrong side. It attaches from the other end. So it actually attaches from here. Okay, let me use a different color for that. Okay, and then over here, we could have whatever else, right? Like you can keep going. Okay, so that means that we start. So here we're starting at the carboxylic acid end. And we're building up. We're building towards the nitrogen end. In the context of proteins, and maybe again, you maybe have talked about this already in some other biochemistry class, or you will, but this is called the N-Terminus. And this is called the C-terminus for self-evident reasons. Yeah. And then the point is just from there, right? Once you're adhered, you know, you could just draw your bead. You don't have to like get that fancy about it. So for stereochemistry, this should be pointing out like this. Okay, and so you have a free amino acid hanging off, and so you want to protect it. Okay, so step one is to protect it. You could often use FMOC, which is like what the thing is called. So it's FMOC chloride. There's an alternative. You could use something called BOC instead of FMOC, either one. So you can protect. Okay, FMOC is like huge. It's like a really big thing. Yeah. Oh. Sorry, this should actually have had an FMOC on it. That would be why the nitrogen doesn't attack already, because it is the better nucleophile, but it has a protecting group on it. So if you have a long chain, then you want to protect, and then two, although maybe I have this order kind of wrong. So yeah, I guess the order is wrong. Maybe let me move these around. So this thing should go up here. Well, I'll move it down here. So protecting should actually be later, or kind of separate. So we'll protect later, and then, oops, messy. So up here, okay, let's get back to this now. So one, we are protected now, which is what I should have had earlier. So one, we should deprotect because we want to do a reaction on it. Okay, yeah, there we go. So here we should deprotect, which is really easy. You just give it piperidine. Okay, and this happens in DMF, although I think all of this happens in DMF. So this deprotects. Oh, that's not correct. Yeah, so O, there we go. Okay, cool. So now we have an NH2. Okay, cool. Great. So now we deprotect. Now we activate. Oh, keep getting this wrong. Here we go. So now we activate. By adding DCC. Okay, which looks like, I'll write CHX for cyclohexyl because it's way smaller. And there's a double bond to C and one to here, and there's another nitrogen on this side. Okay, and the idea is that here we have our bead, right? Great, our whole amino acid. Drawing these gets very tedious. But of course, let's use this color. So this is like a really good nucleophile, and so it's going to attack onto that carbon because that carbon has effectively like 2 carbonyls or 2 imines on it. So it's really, really good electrophile. So we have this, right? And then there's the carbon. There's the N cyclohexyl. There's an NH cyclohexyl. Okay, cool. And now, let's see. So, yes. And then, oh, this should happen from the end, from the C side. Oh man, I have it out of order. Don't I? Yes, I do. Ah. Yeah. So what you should actually do is not the one with the bead, but a separate amino acid in like a separate sort of flask or container. All the reactions, I guess, one you could remember it by a way you could remember this is that all the reactions happen at the carboxylic acid side. So here, right, you have this O minus, and then let's redraw the structure here. So we had an O here, and then an R, and then an NH2. Although this, I think, should probably be protected. Yes, indeed, actually it should. So this is a protected NH2, or NH rather. And so here we go. We have this whole thing. This should well, okay, yeah. So we have this, and then what we're finally getting to is the point that this is really similar to an anhydride. So this is like very nice and well and reactive. And at the end of the day, the point is that we have this deprotected, amino acid on the bead. Okay, and so for our last step, step 3, we couple them. And so here we have now, now we add these two things. Okay. So this is an N and a cyclohexyl, and here's an NH cyclohexyl. And finally, we can just do this. Come in, kick these electrons up, kick them back down, and then send this leaving group on its way. Okay. And now finally, after all that and all that confusion and everything, we've added a second group. We formed an amide. We have this new R group, right? And then it's protected. So it has FMOC again. And so now the end of the chain again has FMOC, and so we can go back up. So we could deprotect it from the, take the FMOC off, activate a different amino acid elsewhere, and then add it. And so then at the end of the day, we go back. Okay. That's all the reactions. This one, solid state synthesis, gets complicated. At the end of the day, when you want to take the protein off, So when you want to take the protein off, you have this bead, right? And then you have this whole like protein. Right? This is a protein. It's this whole complicated, you know, tied up mess. You just add HF. It's really nice. You just kind of add HF, and that's it. So that's all you do. Yeah. Okay. Well, let's do some problems because that was a lot of talking, or me talking. And oops. Here we go. All right. So we will do some problems. I need to pull up the problems. Okay, this is a large, like a roadmap sort of thing. These are always very fun. Oops. Okay. Okay, so let's see what we're working with then. There's this creepy dude. I'm not sure why. Sure. So okay, well let's fill in then. Here's let's say that we want to fill in this arrow. So we have bromoethane, right? And we want to go to this carboxylic acid. What do you think we should do?
Well, you could do just regular SN2 to add a CN, and then hydrolyze that with
Sure. Yeah.
acid, right? And then that'll add your extra carbon.
Yeah. So we use HCN and KCN, just because that's sort of the common way of doing SN2 with cyanide. And then 2, yeah, we just hydrolyze it. Sure. Yeah, that's a good way of doing it. I also thought there's another way. Another way you could do this is also just to do to make it a Grignard. So 1 magnesium, 2 CO2 is another option. Either one is equally as good. So
Cool.
Yep. Yeah, but it's just I only mentioned the other one because it's just good to have more tools at your disposal.
Totally.
Yeah. Okay. Well, how else could we have made this thing? Through ozonolysis. And so what could we have cleaved in ozonolysis to make an acid?
It's been so long since I looked at that. Some kind of double bond. I can't remember if it's just like a an alkene or if it has to be like a ketone. I don't know. I think it's just an alkene, right? And then you'd have to, oh, but this is just,
It's just water.
right.
Yeah.
Right.
Yeah, and with those analysis, I think normally you'd have to do some sort of oxidative workup to get an acid. So you would normally use like hydrogen peroxide, but here we're not.
We have quite a few revisions to do before final.
No, so this is so in this case you could use an alkyne instead.
Oh, right. Oh, God, I haven't thought about
And so here it,
forever.
this side, I mean, it doesn't matter what this side is, I guess, because it's going to be just trashed. So you're just doing that to get this thing, which is called propionic acid, I think. Yes.
Right.
That's an option. What about this one?
That's the HVZ.
Yes. Yeah. And what you were going to say right before you said it. So, especially because this is like such an absolutely like telltale
Yeah.
thing. Yeah, let's see. What are the reagents? Let me look them up. Okay. Yeah, because I can never remember them. My HVZ is one of those that's like so well named that.
Yeah, it's just easier to remember HVZ. Right.
Yeah. Although I think we do need to put the reagents. So yeah, it's BR2 NH BR3 or PBR3 and water. That's what it looks like. Yeah. Okay, up next.
So that's just going to do a substitution to BR.
Yep. This is not a very sophisticated one. Okay. And okay, well, what do we add to this then to make it NH2?
Just ammonia, right?
Is it ammonia? So I actually can't remember. This is one of the ways of synthesizing primary amines.
Right.
Where you just do SN2 with azide and then you do something afterwards. I think here we want some kind of reducing agent.
Okay.
To reduce azide, although I can't remember exactly. This is something that's worth checking.
I could pull it up in a second. I have like a set of notes in front of me.
Sure.
Let's see. Oh yeah, yeah. So you need to reduce with either hydrogen and palladium or just like LAH and water.
Okay. Yeah. Okay. So yeah, so you could just reduce the azide. What a nice way of, I guess that's a nice way of making it.
Yeah.
Yeah, if you would just have an acid, then you could do this. Yeah. Do you know what the name of this amino acid is by chance? I guess you don't have to remember the names of them, but
I don't know. I want to say alanine, maybe.
yes, it is right.
Mm-hmm.
So this is alanine. Yeah. In some sense, this is the most basic amino acid. You can make the case that, let's see, this was drawn this way. So you can make the case that this guy, glycine, is the most basic amino acid. But depending on how much biochemistry you've seen, glycine is actually normally classified as like a special case of amino acids.
Right.
Which has to do with the fact that there's no side chain here, which means that you have like really easy free rotation around here. And when you have like that means there's a lot of entropy in glycine. And so for example, glycine, whenever, if you like you can't have glycine in like an alpha helix or a beta sheet, really. Beta sheets you might be able to, but yeah, they're bad for alpha helices because they hate to be confined or like
right. That makes sense. Yeah.
So, well, yeah, in some sense this is simpler, but it's also kind of not. When people are doing studies of proteins, they if they want to find if an amino acid is important for their structure, they usually replace it with alanine because it's sort of like the most benign, unchanging thing. What about this thing? This abomination of an amide.
Yeah. Ugh. I don't know. You'd obviously have to open that like weird ring. But I don't know what the easiest to do that would be.
Okay. I mean, what's one thing that breaks amides?
I know it's like a really simple answer and I just am not thinking about it.
Yeah, it is.
I know, like at this point in the semester, I'm just like so brain dead that.
Yeah. Yeah, I get it. I mean, well, we want to add, let's see, I mean, what are we working with, right? We have this part. We have the NH. We have the carbonyl. It's just here they're connected. Right. So we want to add, and this will give it away. So here we want to add.
It's an acid?
Yeah, just give it acid. So here we want to add a hydrogen. Here we want to add an OH, right? So.
Okay, yeah.
Just give it an acid. Yeah.
Probably the simplest possible answer, but absolutely.
Yeah, I know.
Acid.
Yeah, and it works nicely too because this is like really ring strained, so
you wouldn't really need
just
a lot
stick
of
it in
energy.
water.
Yeah.
Yeah, just pop open. Yeah, there's not that it's that related to amino acids, but there's a separate sort of thing. There's like a whole class of antibiotics which are called beta lactams, which like penicillin is one of them. And so the main structure of them is it has this 4-membered ring which has an amide in it, in large part because like I don't remember exactly in what way, but this sort of thing mimics an amino acid because it has a carbonyl next to an amide. And there's And a lot of bacteria and things are resistant to ampicillin or penicillin or all of these beta-lactam antibiotics. And the way that they're resistant is that they just have an enzyme which sticks water in there and breaks it.
Interesting.
So, yeah. So that's a fun fact. That's how a large amount of antibiotic resistance works. Of course, there's plenty of other types of antibiotics, but yeah. And this thing inhibits protein synthesis because it looks like an amino acid. So bacteria try to stick it in proteins, and then it breaks. Yeah. So. That is a fun thing. I want to move this thing slightly. Okay, Control R. That's what I want to use. Okay. Oops. Second. Okay. Nice. I finally got that set up now. Okay, cool. This thing looks too complicated, so maybe let's avoid it for right now. Let's go over here then. We want NHC, NH3, and HCN. So
That's a Strucker. So you'll just need to add like an aldehyde that would get you there. So I guess that would be just the acetaldehyde.
Yeah. So that's just Strecker, and from here to here, what was the next part? Step 2 of Strecker?
Oh, sorry, acid. I was muted.
Yeah, it's just acid.
Acid.
Yeah, okay. And then, okay, well, what if we want to go backwards?
Yeah.
Oh, that's a kind of hard thing.
Yeah.
If we want to go back, yeah. I guess somehow we have to go from this acid up to a nitrile.
Yeah.
What is a good way of doing that? Yeah. So if there's, let's say, if there's some way to turn this acid into an aldehyde, right? If we turn it into this aldehyde, then we can give it NH3 and then not really. I don't know if you could oxidize amines. I guess you can, but like not really. No, I guess that's not it.
I know that there's like a way to get directly from the acid to the nitrile. I forget, it has a specific name, but I forget what it's called. And it has like not KCN, maybe KSCN or something. But this is obviously 2 steps, so it's clearly not what they're looking for.
Okay. Well, no, yeah, having a 1-step way of doing this would be even better. I've forgotten about this, but I think there's a way. So I can't remember if this is a type of reaction, but if there's a way to turn amides into nitriles, right, from here. So here, this is easy because you just dump ammonia into it. I think there's something that lets you go up this way. Although I can't remember what. So I'm checking for what reactions there are with nitriles, trying to make them. Because I think deprotonating one of these nitriles is like, or one of these amides is like the only way we have to actually make a nitrile.
Yeah.
Let's see. So nitriles, you could react them with Grignards, but that's not what we want. Some stuff about anhydrides and esters. Is there something about amides? Yeah, there's something about amides. Here we go.
Is it P4010 or P205 or whatever?
Yes, exactly. Yeah.
Okay.
I just found it. So it's P205. Yeah.
Good.
P205 or POCl3. Yeah. Yeah, that's the way to do it.
Cool.
Okay. Gross. Okay. Over here, we're doing reductive amination. So this compound is what?
Your amine.
Yes. H, yeah. There's a reductive amination. Okay, cool. Let's say we want to go from alanine down to here, which is adding an entirely new amino acid. No, is it? Yeah, it's adding a second alanine. Disgusting.
Does it want you to write out like what all the steps you would do for a solid phase? That seems sort of ridiculous, but I don't know another way to like couple two.
So since we're just combining 2 amino acids, I don't think you have to do all the. I don't think you have to go all the way to do solid state.
Okay.
In fact, what you said, I think you could just do the coupling reaction.
Oh, right.
I think it's actually enough to just add DCC. Yeah. Maybe you need like extra a second step or something, but I think just DCC and then water maybe afterwards should do it. Yeah, let me check the key on this one because I think that should be plenty. Should work. Okay, yeah, it's just an equivalent of DCC. Excellent. Okay, and then lithium aluminum hydride and water. What will that do? Lithium aluminum hydride does something with esters, right? Not esters, amides.
Yeah, I mean, I assumed that it would just reduce.
Yeah, either that or it'll just reduce the acid. And possibly this carbonyl too. I can't remember the reaction that lithium aluminum hydride does on amides. Let's see.
Yeah, so I'm looking at this under acylation reduction back from chapter 19, I guess this is. And then when you have the amide, adding LAH just reduces off that carbonyl, just takes off the ketone. For the, yeah, so it goes from amide to just the amine. So I guess it would just take off that carbonyl.
Oh yeah.
Yeah, I mean, you would think though that wouldn't, oh, maybe not. I was gonna say, wouldn't LAH also reduce the carboxylic acid or no?
I think it will also reduce it. Yeah, I think so. Because there's like there's not really selectivity between these two. Like,
yeah.
Both. Yeah, so.
Okay,
I think so.
Cool.
Yeah. Yeah, I was looking in chapter 21 and I found the same reaction. It's like a callback to like the chapter 19 reaction. Although I was like misreading it. So nice. Yeah. Okay, and then we kind of skipped this one because it looked too complicated, but maybe it's not.
Oh, that guy is ooh. The Gabriel Synthesis? Yes. I have it written under like this weird, yeah. Does an SN2. Yeah, I guess it would just take off that bromine and add itself. And then the K2CO3, I don't really know what that would do there.
It's just used in the Gabriel. It's just used to attach this in the Gabriel synthesis.
Oh, I see. Somehow I don't have it written down. Okay.
Okay, so this is just attached. And then there's a ring. Cool. And now up here, we want to add this carbon. Oh. This guy. Okay.
Mm-hmm. So would you first need to add a base to take off that hydrogen in between the two esters? This is definitely a chapter 22 deal.
Yep. Yeah.
And then I guess you could just add like, methyl iodine or something.
Yeah, that's exactly how I would do it. I wrote a really weak base because
Sure, yeah.
this is going to be really acidic.
Acidic,
So
yeah.
yeah, maybe you could use, maybe there are better bases to use. I guess you could just use like NaOH and it'll go. I guess you could just use this and the reaction will go to completion, and then you just use methyl iodine and you're done. Okay, and then from there we are doing what? How do we get rid of this?
Yeah.
This is totally some chapter 22 reaction.
No, I already blocked that out of my brain.
Yeah, I know. I wish I could.
Oh shoot, I know what it is. Hang on. Right. Okay. So Malonic Ester synthesis.
Yes.
I got there finally.
Yeah. Yeah, this is effectively Malonic Ester. Technically, I think Malonic Ester should have actually, anyway, it doesn't matter. Yeah, so what are we doing last step to get this acid left over and get rid of the junk?
Yeah, so just acid and heat. Heating causes the diacid to break apart.
Yep.
Yeah.
That's it. Yeah. Half the reactions in this whole thing are just acid and heat. So yeah.
Cool.
Okay. Good. Let me grab
Nice
some.
sort of review from a lot of different chapters ahead of the.
Yeah.
You know?
Yeah, they come back.
Unfortunately.
Fortunately, this is about as far as they can go. So after this, it's the final, and then you're done, which is like a real treat. After 2 whole semesters of this, you will never have to do organic chemistry again, unless you want to. But
Again.
huh? Yeah. Yeah. This is also like the part that I like of the semester, because like, as I like to say, at this point, you know as much organic chemistry as I do, so your guess is really as good as mine. And I'm also doing these problems blind too, so we're actually just, in this together.
Solidarity.
Yeah, I know. Yeah, unfortunately, we can't do the quizzes together. So
Yeah.
yeah. Okay, predict the product. Oh, nice. These are fun. Yeah. Yeah,
Right.
I like these. All right.
So the first product is just alanine.
Is alanine.
Right?
Yeah.
Reduction, reductive amination.
Yes, exactly. It is. Yeah. So we do this, we cross this out and just write NH instead. And cool. Yeah, exactly. What's next? Okay.
Not quite as simple.
Yeah, what the hell is this? All right.
I assume this is acylation reduction. So you're right, because you would have your probably the amine reacting with the acyl chloride.
That's what I think, right?
No.
I think it'll come up here and kick off the chlorine.
Yeah.
Right, and so you'll have this, and then the NH over here, right? And then you'll have like this. This is
Nice, nice. Okay.
I was guessing.
I guess this is just the point of the semester where it's like, I'm just gonna throw something at you that you've never seen before, and you just have to like use your knowledge and figure out what's gonna like react first and all that good stuff.
Yeah. Yeah, it kind of is. I feel like I've seen this reagent before.
Yeah.
So I'm vaguely thinking it might have some special function or purpose, but I can't remember. Well, I'm looking, but I'm not seeing anything, so.
Yeah.
Yeah, so this seems like it could be it. This is like a real blind guess, but another possibility is that maybe this thing attacks, these electrons on the amine attack here and kick this off. And so then you've just attached a phenyl group or benzyl group. Why don't I check? Because I think it could be either of those, but this might be some kind of like special reaction. Oh, no, it's just this. Okay, never mind. Oh.
Okay.
Yeah, this is it. I'll just redraw it so that it's not ugly, but okay. There's really nothing special going on.
So you just put like wherever the N-Terminus is gets attached where the chlorine is, and then everything else is just dragged along for the ride.
Yep.
Cool.
Yeah. Yeah, I really thought there might be something more to it, but that is it. Okay. I shouldn't have doubted our intuition. I guess that is it.
All right.
Okay.
This nice, very recognizable reagent here.
Yeah. Yeah, this one is not a surprise. Or yeah, there's like a huge flag.
So admin degradation.
So there are two amino acids.
That weird like cyclic product, right?
Yeah, there's two amino acids. There's this one and wait. Sorry. There's this one, glycine.
Ah, yes.
And then alanine next to it. So this is alanine, and then there's glycine over here. This one over here was valine, just for good measure, right? And then this, originally we made alanine. Okay, anyway. Okay, so I mean, at the end of the day, is it going to pull off glycine or alanine? Because once we know which one, then, you know, we could draw the structure at the end.
So I guess glycine, right? Because that's the N-Terminus one.
Yeah, exactly.
Okay.
All right, maybe I shouldn't try to draw this from memory because it's going to be terrible. So close. So close. There's not an S here, there's an N. With pH, N, C, S. Yeah, that's it. And so here we have glycine, right? And the alanine's unchanged.
So if we had, okay, I see. So then it's also part of, like, you would just draw the what's it called, alanine freely. Yeah.
Mhm. Yeah.
Right. So we would need to draw both. Like if this was a chain of 3 amino acids and we had this like on a quiz or whatever, they would expect to see like the cyclic degraded amino acid and then like the chain of both of the other two.
Yeah, I think they would expect to see the chain.
Okay.
Yeah, acid, I mean, acid is, it can cleave peptides, right? So, you know, you can make the case that like those 2 remaining things would actually be free amino acids, but
Okay.
I think you should write down the chain.
Okay.
Just to show that like you're pulling one amino acid off and then everything else stays the same.
Right. Yeah. Demonstrating the degradation process. Okay. Cool.
Oh boy, what do we have? Okay.
So this looks like
Aniline.
it would be a Strecker, just instead of NH3, we have the phenylamine.
Oh.
Right.
Yeah. Okay.
Aldehyde.
Yeah. No, that's a good idea. I just didn't see it at all. So, okay. So, Strecker normally works by making imine, right? So pH, and then there's an imine. Okay. And then we add this, right?
Cool.
Yeah, I think so. Maybe something went wrong here. Because with Strecker, normally don't we get an imine and then the nitrile and then you hydrolyze the imine. Oh, no, this is right. Yeah, it is. Yeah, okay.
We'd have to add acid after that.
Yes, you're right. So if we were to add acid, then we would get OH, NH2, pH, this thing. Okay. Yes.
Oof. Okay, so this one is the other one with the name. Hydrin.
Yeah. Hydrogen, and I don't know if there's that much to say about it. Yeah, we react and we form Ruhmann's purple, which has a very specific structure that looks like this, and then there's these carbonyls, right? And then there's something like this, and O minus, yeah. Yes, that's it. Plus CO2 plus, there's an aldehyde. What is on the aldehyde?
So presumably it would just be like the rest of your, oh, I don't know. Hang on. So you would just have like your aldehyde is where the carboxylic acid was before, right? And then you have.
Yeah. So, yeah, so that does make the, that makes the aldehyde. And so what's over here?
Just the rest of your chain there, right? Like the phenyl.
Yeah, exactly. Like that. Oh, did I add a carbon? No, that's it. Oh, no, so we did add a carbon. So it's the R group directly on there. So this carbon actually goes away. So you lose this carbon here.
Oh, wow. Okay.
Yes, so there was an extra carbon there. Yeah. In general, if like, you know, if this is the R group, in general, maybe I should use a different color. Yeah, in general, if this is the R group, then you have R aldehyde. So, yeah. Okay. And then one more predictive product. This and pyridine. So this is just here. Oh, this is one of the ones that was like way too boring to talk about earlier.
Oh. So you just acylate the amine, right?
Yeah.
Terminus, yeah. Cool.
Yep. There's really not a lot going on in this reaction. I'll just write CO2H. Yep. So we started with alanine again. Very cool. This is not a natural amino acid, this one up here. So I think so, unless I'm forgetting one, but yeah, that's not a natural one. this is not even an amino acid. Well, it is, but it has a phenyl group on the end. It's unusual. There's a plus here too. Okay, whatever. Okay, and then last thing is there are two mechanism problems. One of them has to do with the Edmond degradation, but since you have your book, I don't know if it's like, well, that's the second one. So I'll leave it for you to decide if that one's worth doing, because, you know, I think when I took the class, I didn't even bother learning that one. And it was an in-person exam. So
All right.
Yeah. Mechanism for this, yeah. So well.
So yeah, let's see.
What happens. So remember the structure of DCC.
So this is definitely part of the solid phase synthesis. The DCC step that will pull the so I guess the alcohol on the acid, so the OH on that acid will do the attack on the C in the middle of DCC.
Yes. Yeah. Or it's this oxygen up here. I think this one's usually the more nucleophilic, but I mean, of course, it doesn't make a difference at the end of the day anyway, because, like, you know, the two oxygens are the same. Yeah, let's see. I'm sure it says it somewhere. I'm looking. Okay, so it uses an O-. I guess if we're drawing a detailed mechanism, then we should probably skip that step. Yeah. So, okay, yes. So step one, water, normal water, not acid. So water will come in, take this guy, right? And then, okay, and then we proceed, right? We just do the next step. So O-, okay, great. And then this minus will come up here and hit this. And then these electrons will go to one of these two, right? There we go. So there's an O, and then this is the nitrogen we transferred to. Actually, maybe let me make that one down here. And then CHX, right? And what do we have to include here? Like there's something missing here.
Do you have to protect it?
Mm-mm.
No. You just need to add the charge on that nitrogen.
Yeah, exactly.
Okay. Overthinking it.
I was missing that. Here's this minus charge, right? And then, well, we don't really like minus charges, so let's donate that to a water. Or use that to rob a water. Okay. Great. Yeah, and so here's this N cyclohexyl, this NH cyclohexyl. Okay, cool. And now what?
I guess. So I'm looking at the next step in what we kind of like went over earlier, which would be to use like another nucleophilic attack and like kick off that whole extra group there with the cyclohexyls.
Yeah, and so that'll be our amine, right?
Oh yeah, yeah. I like forgot to look.
Yes. Here comes up, comes down. Of course, you want to write those out and not be lazy. But I've already taken the class, so I get to be a little bit lazy. Yeah, and so we do that, right? And we kick things off, and okay, we have two things. So now we're left with two products. So one of them is NH2 methyl, right? And this should have a plus. And the other thing is this. Okay, excellent. And we're almost done then. So what do we do? What do we do here? What's left?
So you're just going to need to deprotonate the nitrogen.
Sure. Water. There we go. Okay. Over here. The other one.
And then protonate that. Or no, we got to move that. Move some electrons. So just push those electrons down and then push those electrons back onto the N.
Okay.
And it's going to need to grab a hydrogen.
Yeah. So let's just pluck that off of water right away.
Okay.
And that's it.
Oh, we made it.
Nice. Okay. I can put up the other one, although whether or not you want to go through it is up to you, because it is just the admin degradation, and well,
Yeah.
I would not memorize this.
Yeah, I'm not super super inclined to go through the whole thing. Just because I think, yeah exactly.
Yeah.
If it ever came up, we're just,
Okay.
Cool.
Awesome. Well, yeah, that's the last problem. So we made it through them.
Perfect.
Excellent. Okay, cool. We even get to finish a little bit early today, because I guess there weren't that many problems, so that's good. Okay.
Thank you so much. It's been very
Yeah.
helpful for me to attend these groups with you.
Yeah, I'm glad you found them helpful. That you've
Definitely.
been able to come.
And
yeah,
you're
I don't know.
right. Congratulations on finishing.
Yeah, I know. Thank God. I'm out. Yeah, I can't wait.
And that's fair, but
Yeah, I know. Yeah, I'm looking forward to that. Yeah, I haven't thought about whether I'll do a final sort of review session thing. I don't know if that would be helpful or not.
yeah, I mean,
I have no
I would
idea.
definitely, if you did have one, I would definitely come. I think it would be helpful for just reviewing some just more like going over everything and like looking at things a little bit zoomed out is usually helpful for me going into finals.
Yeah.
Of course, like if you have other stuff going on, don't obviously feel like you have to, but if you do feel inclined to have one, I will probably come.
Okay. Sure. Yeah. Okay. Then I'll yeah, I'll look into doing one then.
Okay.
I don't think I'll have like really anything going on, so
All right, sweet.
so
Sounds
I can
good.
I'll send an email or two about that then.
Okay, perfect.
Okay,
All right,
awesome.
thank you so much. See you then.
Okay. Yep. Bye
All
bye.
right, bye.
Thank you. I was